let's start now problem 2. Okay, this is problem 2. We just started. So we discussed the geometry. Geometry is exactly the same as we did in problem number 1. Loading the same as we did in problem number 1. The only difference is here we are involving the support settlements, and support is D. It is translating towards the right by 0.5 inch and it is settling down by 0.75 inch. Statically, the structure as we discussed, we have 5 unknowns, 3 at support A, 2 at support D, total 5. 3 are the equilibrium equations available. So 5 minus 3 is equal to 2 degrees. So statically indeterminacy, we declare 2 degrees. E is given, I is given, and we find out EI value and kip feet square unit. Hello? Assalamu alaikum. Ma जान करे टिक ते कार कही है उसका रिकॉर्डिंग हम कीजिए. So okay, thank you so much. Hello? Habibullah, can you hear me? And is it visible to the students also?
Yes, sir.
Everything is fine now, right? It is recording also. Okay, so statical indeterminacy 2 degrees. Now we need to now select 2 redundant actions. Vertical and horizontal reactions at D are chosen as redundant actions. Here you can see, and AR1 in the upward direction at D and AR2 to the right, we declare these as our redundant actions. And here we call AR1 and AR2, these are unknowns. Corresponding to them, we go to the original structure and find out where there are any corresponding displacements. AR1, if AR1, our positive direction is upward, so corresponding to this, we have settlement of 0.75 inch in the downward direction. Directions are not matching, so it's negative, we label it negative. 0.75, this is the magnitude of the displacement corresponding to AR1, so we record this value. Then corresponding to AR2, we were having translation towards right of 0.5 inch, so 0.5 inch we write here. Positive, why positive? Because AR2 and 0.5 inch displacement, they are in the same direction. Now, as we will be using kip and feet units, so we convert them into feet. So 0.75 divided by 12, it is giving us 0.0625, and 0.5 divided by 12, it is giving us 0.0416. Step number 1, here we have labeled our unknown redundant actions, and corresponding to them, we have recorded the DRS values. Next, now we go and we analyze this basic determinate structure under the actual externally applied loads, and we will write the capital M equations for each segment. And then we analyze the same basic determinate structure under the application of the unit load at redundant location. So when it is corresponding to location 1, we generate the M1 equations, and when it is corresponding to the M2, AR2, we generate the M2 values, and so on. So here in next slide, we show this basic determinant structure under the actual loads. We have split them. We have opened the joints now. At joint B, you can see we have sectioned this. At joint C, you can see we have opened the joint. Now, it is the same analysis we did in problem number 1. But if you remember from there, we started from D, we went to C, from C we went to B, from B to A. You can start from the joint A also and go in the clockwise direction. How can we do it? For that, we need to analyze this determinant structure under the actual load. So we need to find out the support A reactions. How can we find out? First, we apply the summation of Fy is equal to 0. Now, this fixed support at A, this is taking the whole loads. So the load will be balanced by the vertical reaction at A. Now, if we see the vertical load apply on the structure is 2 times 30. And this 2 times 30, which is becoming 60, it will be balanced here by this 60 kip. So here we show 60 kip. Then summation of Fx we apply, and externally applied load is only this 5 kip. It is rightward directed, so leftward directed reaction here at A. So 5x, so summation of Fx is satisfied, summation of Fy, both are satisfied now. But now we look at the moment now, because support A, fixed support, it can resist the moment also. So let's take the moment about this point A, MA, and MA will be equal to, this will be the balancing resisting moment. It will be equal to 2 times 30. This is the equivalent pointed load. We are taking resultant of this 2 kip per foot, which is at a distance of 30 feet. So 60 is the equivalent, or it is the resultant of this 2 kip per foot multiplied by 30. So 60, and its distance from A is 30 divided by 2. So 60 multiplied by 30 divided by 2 is 15. So 60 multiplied by 15 gives us 900, plus this was causing clockwise movement, plus this 5 times, and this 1575, it is also in clockwise direction. So 900 plus 75, 975, it is clockwise, it will be resisted by this 975 moment at support A. We ignore all these other calculations. You see here, this is coming from the previous one when we started from D to C, C to B, and like that one. But now we want to move from this A to B and so on. Now we found the support reactions at A. Let's start moving towards B now. This member AB should be in equilibrium. When this will be in equilibrium? When upward force at A is resisted by B in the downward direction. So 60 and 60 summation of Fy, this is satisfied. Summation of Fx is equal to 0. We have 5 kip here, leftward directed, and 5 kip we should be having rightward directed. And if you remember, this 5 kip, it is externally applied, this red load. It is not internal load, it is externally applied. Moment here, it is 975. So moment at joint B will be 975. It is counterclockwise, minus 5 times 15. So minus 75. So this 900 now, this is the balancing moment here. The difference which is here, it will be resisted here. Now joint B should be in equilibrium. So 60 we have downward. So 60 we should be having in the upward direction. 5 kip, it was externally applied load. So internally, if you see, we have 0. So 0 will be transferred here. Horizontally, it is in equilibrium. Then moment, it is clockwise 900 kip feet. So 900 counterclockwise, joint B is in equilibrium internally. Now let's put this member BC in equilibrium. So 60 in upward direction and 2 times 30, 60 in the downward direction. So here the balance will be coming at C now, which is 0. 60 minus 60 is equal to 0. So upward here is 0. Horizontal at B is 0. So horizontal at C also 0. Summation of Fx is equal to 0. Moment to find out MC now. So MC will be equal to minus 900. And then we have plus 60 times this 30. And then we have 2 times 60 times this 15. So if you add them up, it will be giving you 0 value, and that 0 we are showing here. Joint C should be in equilibrium. So vertical and vertical 0, horizontal 0, moment and moment 0, all are 0. Now member CD should be in equilibrium. So all the actions at D are 0. So you can start from A and can start moving towards B, C, and D, and you will get exactly the same values which we found the other way. Now then we start writing the moment equation. Moment equation already we discussed. We need to first select the origin in such a way so that we get minimum number of the moment components. Now here, if you see this 5 times x, we are taking A as origin for member AB. So 5 times x, it is causing compression, so with positive sign, and minus 975. So this is causing tension. So this is with negative sign. So MAB is coming 5x minus 975. For member BC, we are taking C as origin. So when we take C origin, this shear is not causing any bending moment. Axial, it is not causing any. This, at the end, we don't have any moment. Only this UDL is causing moment about this section X. And it will be 2 times X. This will become equivalent pointed load, or this will become resultant of this span X having 2 kip per foot. So 2 times X, and the distance will be X divided by 2. So 2x squared divided by 2, and from where this negative sign is coming, this is coming again. This moment will be causing tension at the outermost fiber, which is the topmost fiber in this case. So that is why we have minus 2x squared divided by 2 means minus x squared. 2 and 2 are getting cancelled. For CD, we took D as the joint. And here the shear is 0, axial is 0, bending moment is 0. So the whole MCD or MDC is becoming equal to 0. So this way we generate our capital M values. And remember again, the capital M values, they are generated from the basic determinant structure when it is analyzed under the actual applied external loads. Any question? CR, if there is a pause and if there is no question, then you should acknowledge that there is no question so that I can proceed. Otherwise, I'll consider that if there is no question and there is such, let's say, silence, so then I'll consider there may be a network problem.
Okay, sir, inshallah.
So should I proceed now?
Yes, sir, you can proceed, sir.
Okay, so we go to the next slide now. Here now, the basic determinant structure is acted upon by unit load at redundant location 1. What was the redundant location 1? If you remember, AR1 was the vertical reaction at D, and it was in the upward direction, AR1. So corresponding to that, we are applying this 1 kip. Now again, let's ignore all these member inductions and we start moving from this support A. So for that case, we need to find out the support reactions. How we find out the support reactions? This is the only external action now applied 1 kip, and it will be resisted by this support A. So summation of Fy if we apply. So summation of Fy if we apply, it is 1 kip in upward, so 1 kip in the downward direction. So we found the vertical reaction at support A. Horizontally, there is no external load, so horizontal reaction at A will become equal to 0. About the moment now, this 1 times this perpendicular distance up to this A, we are finding out MA now. So this will become 1 times 30. So this is 30 cube feet and it is causing clockwise movement. So it will be resisted by the counterclockwise, which is 30 cube feet. So we found all the support reactions at A in this determinate structure, which is under the action of 1 kip load. Now, let's start now analyzing each member and each joint. AB, let's analyze this 1 kip in downward direction, so 1 kip in upward direction at joint B. Summation of Fy is satisfied. Summation of Fx, 0 at A, so 0 at B. Summation of Fx is satisfied. Moment, 30 kip foot clockwise, so 30 kip foot counterclockwise. If you look at this, member AB is in equilibrium. Giant B should be in equilibrium. 1 kip in member AB at B in upward direction. So for BC at B, it will be in the downward direction. Giant B, summation of Fy is satisfied. Horizontal 0, so horizontal 0 here also. 30 counterclockwise, 30 kip foot clockwise, so moment wise also this joint B is in equilibrium. Now let's put this BC in equilibrium. So 1 kip in downward direction, 1 kip in upward direction at C. Summation of Fy satisfied. Horizontal 0, moment. 30 kip foot, it was a clockwise movement. So now this 1 times 30, it is causing counterclockwise. So 30 minus 30, 0. So that is why here we have this 0. Giant C should be in equilibrium. 1 kip upward, so 1 kip downward here. 0, this is 0, moment is 0. Now this member CD should be in equilibrium. 1 kip in downward direction, 1 kip in upward direction. Horizontal 0, moment 0. So moment is also 0 here. Now each member and each joint is analyzed. Now remember, once we fix these origins for the capital M value, we will have to follow those origins. Now we cannot now change those origins. So for AB, again, we are taking this A as origin. Moment is 0 times X and plus 30. So 30, M1 for member AB is coming 30. This is the moment equation. And it is applicable throughout this AB length, which is 15 feet. And its I is only single I. Coming to BC, taking start from C as we did for capital M values, the moment will be 1 times X, Y plus, because it is causing compression in the outer fiber, and the moment which is causing compression in the outer fiber, we take this as positive. So 1 times X, so X we are recording in the other moment is 0, so no need to write it. Then M1 at CD is equal to 0. So now we have here again D as and capital M. We are taking this origin. Shear times this distance, shear is 0. So we have 0 times X, so 0, and the moment is also 0. So it means the whole moment equation is becoming 0. So M1 for CD is becoming equal to 0. Quickly you write these values. You can write here also, you take out your pens and write that MAB is equal to 5x minus 75 and origin is A. So that when we get to the table, so that you understand that how we fill out the table. For BCC is the origin and MCB, the moment equation is minus x square. For MCD, the D is the origin and the moment equation is 0. Similarly, for M1 values, for member AB is the origin, moment equation is 30. For BCC is the origin, moment equation M1 is X, and for CD, D is the origin and the moment is 0. Next, now to generate the M2 values, to write these M2 equations, What we do now, corresponding to AR2 in the same direction, we apply a unit action, which is 1 kip. Rightward directed as AR2 was also rightward directed. Let's ignore all these member and actions, and we start this in a other way now. We first find out the support reactions. We take that particular element and then we start and analyze each and every member and joint. Now to find out the support reaction A, this is the only support now, which is fixed support. It is taking all these externally applied actions, the effect of all these externally applied actions. 1 kip to the right, so 1 kip to the left, summation of fx is satisfied. Summation of fy, we don't have any vertically applied load, so this vertical reaction at A is becoming equal to 0. To balance the moment now at this A, this 1 kip, it is passing, if we extend this line, it is passing through this A now. So it means the perpendicular distance about A is equal to 0. So 1 times 0, it is generating 0 moment about A. So that is why the moment here we declare this equal to 0. Now taking start from A, and we put this AB in equilibrium. So 0 upward, so 0 here also at B. It is in the Y direction. Summation of Fy is satisfied. 1 kip, it is leftward directed. So 1 kip in the rightward direction. So summation of Fx is satisfied. Now this 1 kip and 1 kip, it is making a couple now. We cannot balance this here because from the equilibrium we found this moment is equal to 0. But this is a rigid joint and it can resist the moment, it can take the moment. So this 1 times 15, it was causing a couple of 15 kip in the clockwise direction. It must be resisted by 15 kip in the counterclockwise direction. This is how this 15 kip is coming. Now joint B should be in equilibrium. 0 kip, so 0 kip, 1 kip rightward, 1 kip leftward, and 15 kip feet counterclockwise, 15 kip feet in the clockwise direction. Joint B is in equilibrium. Look, if we start from A and go towards B and from B to C, we are verifying those values which we found when we moved from D to C and so on. Joint B values we found. Now let's analyze this BC member. 0, so here at CZ, 0 summation of Fy satisfied. 1 kip at B leftward directed, so 1 kip at C rightward directed. Summation of Fx satisfied. Moment, it is 15 kip feet clockwise, so at C 15 kip feet in the counterclockwise direction. So this is also satisfied. And member BC, it is perfectly in equilibrium now. Joint C should be in equilibrium 0. So here we have 0 vertical. 5 kip rightward directed, so not 5 kip, 1 kip rightward directed, so 1 kip leftward directed. Summation of Fx satisfied. Moment counterclockwise 15 kip feet, so 15 kip feet clockwise, they are balancing each other. So joint C is in equilibrium. Now CD should be in equilibrium. 0 and 0, we have summation of Fy satisfied. 1 kip, it is leftward directed, so 1 kip here, summation of Fx, that is satisfied for the member. Now moment 15 kip feet was clockwise, so 1 times 15, it is counterclockwise, so 15 minus 15, 0. At free end, you must be having 0 moment, so this 0 moment is coming here. Now to write the values of M2 values for each member, again for AB we are taking A, and moment will be 1 times X. This moment is 0. So 1 times X, it is X now. For BC, origin is C, and moment will be 15. So 15, we write it here. This 0 times x is giving you 0. And for CD, this equation will become equal to 1 times x. So here, x here you see the other moment is equal to 0. Now we complete the bending moment equation table. Remember AB, it was the left column. Origin we took A. Its limits were 0 to 15. The equation was applicable. Moment of inertia was I. Capital M value was minus 75 plus 5x. M1 value was 30 and M2 value was x. M2 value, if you want to set now verify, we can go back to M2 and here you see x. From here it is coming, this x. For the member BC, it was 2I. Length is from 0 to 30. This is applicable. Now, the moment equation, capital M, if you want, so this is minus x square and origin is C. So keeping these in mind, here you see origin is B, 0 to 30, 2I minus x square, M1 is x, and this M2 is 15. For CD, which was the right side column, C was the origin 0 to 15. Not here, this is mistake actually. Yesterday I pointed out here for BC the origin is C now. Somebody should be pointing these things again and again. For here the origin was C. Let me see if I can correct this. This is C origin. And here the origin is D. Now this is correct. So this was basically a mistake. And we have corrected this. Okay, now the origins 2I here was 2I. For this it is I minus x square x, and for each member you can now verify these values. Next, now we have the standard format now for DRL1, for DRL2, for F11, F12 is equal to F21 and F22. DRL1, it is the summation of the effect of all members. I is equal to 1, 2, and where n is the number of members. These are the members now starting from 1 up to m. Here we have 3 members now, so we will be having contribution from all the 3 members. An integral of m times m1 divided by I dx. DRL2 will become capital M times M2. Only this will be the difference, that it will be the product of capital M times M2. Rest of the elements will be the same. Now, from each member, we are writing the contribution now. 1 over EI, we take this common. Member AB was 0 to 15. So here the limits are coming. 5x minus 75. If you remember, we wrote this minus 75 plus 5x. So this is the same for M, capital M for member AB, times M1 was 30 dx, plus member BC was 0 to 30, the limit, minus x square, it was the value of capital M, x was M1, and this was divided by EI, so I was 2I, so that is coming from 2I, this 2 here. Plus, we have the member CD contribution, so there the value of M and M1 was 0 times 0, so 0, that contribution is coming here. DRL1, when we find out this product, integrate this, put the limits and add them up, all the effects, DRL1 is coming minus 523, 125 divided by EI. Now we go towards this DRL2, and DRL2 if we see, it is M times M2 divided by EI dx. So again, from member 1, we have this 5x minus 75 capital M, x is M2 and dx. For member BC, the capital M was minus x square, M2 was 15, and this is from the 2i, this 2 is coming. Plus member this CD, here it is giving you 0 times some number, so 0, so that is giving you the 0 contribution, and DRL2 is coming this number. Now DRL1, DRL2, EI we take common, 1 over EI it is becoming. And these are the values. Now we have the value of EI, so we put this 125,000. So when these numbers are divided by 125, so DRL1 and DRL2, it is minus 4.185 and minus 1.372 feet. These are coming the DRL1 and DRL2 values. Now from the bending moment table, we can find out our flexibility coefficient values also. For F11, we take the product of M1 and M1, and therefore each member we wrote the M1 and M values. For member AB, it was 30, so 30 times 30. For BC, it was X times X, and for this CD, it was 0 times 0. So here again, we take the integral product and putting the limit. So we get F11 is equal to 18,000 divided by EI. Again, remember here, we don't divide this individually by less 125,000 and is equal to and writing the numbers then, because you will be wasting time. So you do it very professionally now so that you can save some time also. You put all the numbers together and all together, then you divide this by 125,000. Here now F12 is equal to F21. This in the middle you see this equation, the basic equation. For F1 is equal to, which will be equal to F21. And here we write, now for member AB we have 30 times X. For member BC we have 15 times X, and for member CD we have 0 times, so this is giving us 0. So F12 is equal to F21 is equal to 6750 over EI. And for F22 we are using this equation, M2 times M2 divided by EI dx, and here is coming that. So for member AB it is X times X, for member BC it is 15 times 15, and for member CD it is X times X now, and limit is from 0 to 15, so it is giving us 5625 over EI. Next, we write now this flexibility coefficient, divide this by 125 because EI value was 125,000. And F value is coming equal to this. So this is the flexibility coefficient matrix now. Now, next we will write now the compatibility equation and apply the principle of superposition. And this is the equation. DRS was equal to DRL plus F times AR. From the rearrangement of this equation, we have AR is equal to F inverse times DRS minus DRL. And this is now in the matrix form. This was the condensed form. Here it is the matrix form. Why we see this flexibility coefficient 2 cross 2? Because the structure was statically indeterminate to 2 degrees. We plug in the values now by putting the values here. Now, why it was 1 over EI? Why it is becoming EI? Because we took the inverse of this one. So it became, instead of 1 over EI, it became EI. And here, remember, it is with multiplied by 1 over EI. No, EI already, so this EI should not be there because we already included the value of EI. So this EI does not have any application because that is already included. So we need to delete this, and this is now the equation. So now when we find the inverse of this and multiply this with this one, so the product is giving us AR1 is equal to 30.62 kips and AR2 is minus 5.32. This negative sign, now it shows that our assumed redundant action direction is wrong for AR2. It should not be rightward directed, it should be leftward directed. Next, we put these reactions on the, now here, on this sketch now, on the structure, and it is now a statically determinate structure. You can find out the support reactions. You can start analyzing this one. If somebody is asking me, you analyze now under this loading condition, you analyze this CD. So what will be the vertical reaction here? The vertical action here, it will be downward 30.62. What will be the horizontal reaction here at C? It will be 5.32 rightward directed. But this 5.32 and this horizontal 5.32, it will be causing a couple now, and that couple will be resisted by a moment. It is causing clockwise, so that will be counterclockwise, and it will be 5.32 times this 15. That will be the moment here at C. Similarly, you can analyze rest of the beams also, but we want to do this with the help of this flexibility method, matrix approach. Now, these member end actions at A, the support reactions, we can find out very easily. What will be the horizontal reaction here? It will be the difference of this 5 and this 5.32, which is 0.32. And it will be rightward directed. Why? Because 5 plus 0.32 rightward should be balanced by 5.32 leftward force. The vertical reaction will be 30.62, it is upward, and 2 times 30, 60 in the downward direction. Means here the reaction will be in the upward direction to balance this 60. We already have this 30.62. So it will become 29.38. This will be the vertical reaction. You can find out the moment, what will be the moment here. So this is causing 5.32 times 0. It will cause 30.62 times 30 clockwise. 2 times 30 times 30 divided by 2. It is clockwise, and 5 times 15 clockwise. Whatever balance, whatever the difference is coming, that has to be balanced here by the support A, and that will become your resisting moment here. Each member and each joint you can analyze by using the equilibrium method. Now let's AB we want to take, and we want to analyze this by using this matrix approach. So how can we do it? Now the equation is for the member end actions, AM is equal to AML plus AMR times AR. It is a 2D frame member, so each end will be having 3 member end actions. It will be axial, it will be shear, and it will be the moment. And here you can see. Remember again, this labeling and these directions, these are arbitrary. You can choose any one. I prefer to select my positive directions upward, rightward, and clockwise as my positive. Here, AM1, if you see, it is the axial force at A directed upward. This is my positive AM1. AM2 rightward, the shear, and then clockwise movement, it is AM3. So upward, then rightward, and then the moment. This is now my order of these AM1, AM2, and AM3. At B now, when we come upward, rightward, and then movement, again that order is followed. So AM4, AM5, and AM6 we have. Here now I have fixed my positive direction. So my AML will be having the same positive directions and my AMRs will be also having the same positive directions. If they are coming in these directions from, this is now the base for the positive directions. This is the reference. So those will be positive. If they are opposite, they will become negative. Now let's find out the AML here. We need to find out AML now and AMR matrix. AR already we found. AML, it will be coming now from the analysis which we did for writing the capital M values. And capital M values, how we did it? We analyzed the structure, the basic determinant structure under the actual applied external loads. So, and still you will be remembering that the vertical was, upward 60, horizontal, it was leftward 5 kip, and the moment was 975. So here you can see that situation here, 65, 975, and this joint B also be analyzed. Remember, when you are sitting in the examination, you don't need to redo this process here. These two sketches you don't need to draw. Already those were drawn when you were writing the capital M value. So you can flip your 1-2 pages, you can get there and you can pick your values from there straight away, and you can complete this AML matrix, which is a column vector. Now here if you see AML1 again corresponding this to the AM1 value, this is to the AM2, this is to the AM3, our positive directions. Now you match this to this one. AML1, if you see, it is upward is positive, 60 is upward, so we write this positive. AML2 rightward, but here 5 from the actual analysis, it is leftward, opposite to this one. So it means it is negative, and -5 we write here. Moment clockwise, AML3 was positive, but from actual analysis, it is coming 975. It is coming counterclockwise, so -975, so that value is recorded here. Coming to AML4 now, 60, opposite to this one, so -60, it is recorded here. This is +5 recorded here, and this is +900, it is recorded here. Any question now about how we pick the value and its sign?
No, sir. So no question.
No question. Okay, clear, good. We go now to the generation of the AML values. So compute the AMR values. Now AML is already done in the previous slide. So this is when we apply a unit load corresponding to the redundant location 1. And that will complete the first column of this AMR matrix. This 1, 1, 1 subscript, it is showing the location of the redundant action, unit redundant action 1. And 1, 2, 3, these are the now the locations of interest. Here now you see AMR 1, 1, AMR 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. Now this is coming from where we apply at redundant location 1 the unit load. So this was the analysis of member AB. Now to complete the first column directly, I am now telling the values. This should be -1, 0, and 30. You should be verifying these when I'm saying this, so you should be verifying this column. So -1, 0, and 30. And here we have 1, 0, and -30. Minus y, this is counterclockwise, but our positive direction is clockwise here. So 6, 1. AMR 6, 1, it should be -30, which is recorded here. First column is complete. Now, redundant location 2, we applied the unit action and we analyzed this AB, and that condition is shown here. This is that condition. Now, to complete the second column, you should be verifying when I'm saying these values, so you should be verifying these values here, looking these values. So we have 0, -1, and this moment is 0, then 0, 1, and minus 15. So this column is complete now. After this, we write these AML and AMR values here at their locations. We find out the product of these two, add this with this one, and thus we find the AM values. So here the AM values are coming now. AM1 is 29.38. And remember, I told you from the simple equilibrium analysis that AM1, which was the vertical reaction at A, that is coming 29.38. AM2 already I told you that it will be 0.32 rightward directed. AM3, we various components, products we found, we add them up that this is positive, but we did not find the final number. So you can verify this minus 56.4 from there. AM4 and AM5 and AM6 also. Now you can write quickly these numbers and let's see how we put them on the element then. So write down AM1, AM2, AM3, 29.38.3. And 56.4, and then AM4, AM5, and AM6 minus 29.38 minus 0.32 and 61.2. Now we put these memorand actions on the element here. Now this was my AM1, 2, 3, 4. This was the reference. So AM1 it is coming 29.38. AM2.32 and AM3 it was coming negative now, so we reverse the direction and it is 56.4 kP. Now AM4 it is 29 point, it was coming negative, so we reverse the direction. Let's verify this. AM4 minus, so that is why we reverse the direction. Even AM5 FUC we reverse this direction also. It was rightward, so we made this leftward. And AM6 is positive, so we put them in the same clockwise direction. Look for any load before trying the shear force and bending moment diagram if there is any externally applied load on the member. As on member AB, we don't have any externally applied member load. So now we are in a position to draw the shear force diagram and the bending moment diagram. Because of 0.32, this is 0. Now this is the baseline. We come to the right by 0.32. It is pushing this to the right by 0.32. We don't have any load, so it is constant. And because of 0.32, it is coming back to its 0 position. Shear force diagram is drawn. Because of this bending moment, it is causing tension in the outer fiber. So here, 56, we are pushing it to the right. 56.4, and this is also causing tension in the outer fiber 61.2, so pushing to the right 61. Now it is 0 degree, this has become 1 degree. Now member AB is fully analyzed and we have drawn its shear force and bending moment diagrams also. Any question? Okay, now we go to member BC and we will be now repeating the same procedure. So this is member BC now, again, upward, rightward, clockwise, upward, rightward, and clockwise. These are the member actions. At each end, we have 3 unknowns. So these are now my positive directions and these are the labels now. So 6 member end forces are unknown. Now, AML values here, if you remember, for capital M, these were the member end actions we calculated. Now we complete the AML matrix now. So 60, 0, and minus 900. So 60, 0, minus 900 here you see. And then 0, 0, and 0 here you see. This is how we complete the AML matrix for member BC. Next, AMR first column. So AMR first column will come from where we calculated the small m AM1 value. This is the BC now. These are the positive references now, the labels and their positive directions. AM11, it is -1. AM21, it is 0. AM31, it is 30. And here you see these numbers in the first columns. Then AM41, it is 1. This one is 0, and this one is also 0. So here the first column of the AMR matrix is complete. Now to complete the second column of AMR matrix, we go to the M2. There it was analyzed. You don't need to do anything else. Just go there and pick these values. So 0, -1, and 15. So 0, -1, and 15 you see here. Then 0, 1, and -15. So 0, 1, and -15. 0, 1, and -15 you see here. Rest, we apply the equilibrium equation now. Here, AMR matrix is complete now. Now, AM is equal to AML plus AMR times AR. Now, find the product, addition. So, we get this value. Now, if you remember, this AM1, AM2, AM3, this should be the same for AM4, AM5, and AM6, which we did for member AB in the previous slides for member AB. But it should be having the opposite directions. 5.32, it was 0.32. Why? Because this 5 is coming from the external load. And this now, once you found this member AB, the B and forces, you don't need to do it for the BCF. You don't have the time. Already you found the values. So from equilibrium now, you can find out the B and B forces for BC from AB. Now, this one, now we need to put this on the member now. So here we have all these member and forces now. Let's see if this 5.3, this was our AM5. So it should be negative. Why? We have reversed the direction. So let's see that you see -5. This is AM5. Now, we cannot draw from this directly now the shear force and bending moment diagram. We need to put the externally applied loads also. So for that case, we are putting now the member end actions and the load also. And here, this is now the shear force diagram, and this is the bending moment diagram. Now, you can ask me if you have any question in drawing. It is coming from your previous semesters now, how we draw. If we analyze a structure, how we draw the shear force and bending moment diagram. So do you have any confusion now, or do you need any clarity?
No, sir. No, sir.
No, sir.
Okay, this is clear. So we have analyzed member BC also. Similar procedure is now repeated for member CD. So again, we label now the member end actions D. You see here upward, rightward, and then clockwise, AM1, 2, 3, 4, 5, 6. Here you can see. And we designate them as our unknowns. And this is now our reference for the positive directions. Capital M, from there we pick these values. If you remember, all these were zeros, so we record them here. This column is complete now. All member end actions are 0. AMR, so we refer to the small m1 value. And here AMR11, it is 1, 0, and 0. Here you see these values. This is -1, 0, and 0. So -1, 0, and 0. From M2, we complete the second column. This was the situation. So we have 0, 1, and 0. So 0, 1, and 0. And here we have 0, -1, and 15. So 0, -1, and 15. Now, we put them in this equation. AM is equal to AML plus AMR times AR, and we find out all the member end actions. Now, member end actions we don't have any member load now, externally applied member load. This way we complete the shear force and bending moment diagram. For each element, we got the shear force and bending moment diagram. We just superimpose them now on the members, and here we draw the combined shear force and the combined bending moment diagram. With this, now we have completed our problem number 2. What was the basic difference? The basic difference in problem number 1 and 2 was how we handle the settlements if settlements are involved in a frame problem. Should we move on?
Yes, sir.
Okay. Let's go to problem number 3 now. Analyze the given frame using flexibility method. Again, AB, it's a vertical member having 8 feet length, and BC, it's a horizontal member which is having 16 feet length. Here you can see the dimensions. Location A, this is B and this is C. AB is having I while BC is having 2I. The only loads are applied at the joints. At joint B, we have rightward directed 5 kip and 10 kip in the downward direction. EI is equal to constant. It is not constant. Why? Because for BC, we have 2 EI, and for AB, we have only EI. So this statement, this is kind of misguiding. I and 2I directly they are giving for the members. Again, first thing we need to start with is the statical indeterminacy. 3 support reactions are unknown at A and 2 support reactions at C. So the structure is statically indeterminate to 5 minus 3 is equal to 2 degrees. And here we declare that this structure is statically indeterminate to 2 degrees. And based on this statement, now we need to select 2 redundant actions and remove it to make this as statically determinate structure. So if we remove the support reactions capability at C now, this will become a cantilever frame now having only fixed support at A, and that will become our basic determinate structure. So here now intentionally look, AR1 if you see downward and AR2 now we are selecting this leftward directed. Why? These are just opposite whatever we did in problem 1 and 2. This is just to show you the freedom, just to show you the liberty that initially you can assume any direction. Don't think and don't waste time whether, oh, this is going to be positive or this is going to be upward or downward. This is going to be leftward or straight away you take one direction and that is becoming your positive reference then. Finally, you will get a result. If it is positive, it means your assumptions was correct. And if it is becoming negative, just you reverse the direction because it is showing you the magnitude will be still okay. Now AR1, AR2, we are now these are our unknowns, and DRS1 and DRS2 as we don't have any precondition, pre-settlement corresponding to these redundant actions, so we declare them equal to 0 and 0. Now this is our basic determinant structure, which is also known as primary structure or release structure. Now coming to the analysis step 2 part. So it is a 2 degrees indeterminate. The structure will be analyzed 3 times now, one under the actual loads and then turn by the unit loads corresponding to the redundant actions. So that process is written here. Capital M values we need to generate, small m1 we need to generate, and then m2 values we need to generate equations. This is now, we start under the actual load, we start from this BC member. So at C, as there is no load, so all the member and actions at C 0 and all member and actions at B also equal to 0. Member AB, now this 5 kip, it cannot be put on this BC member because we have removed the resisting capability here. It can be only resisted at joint A now. So B, this 5 kip externally applied load, it is rightward, so summation of Fx will give you this 5x leftward directed here. This 10 kip, it is downward, so 10 kip in the upward direction. Let's look at the moment now. So 5 times 8, it is giving us 40 clockwise, so 40 counterclockwise. This is the support reaction at joint A. Now, we write the capital M values now. Member AB, we start now with writing the equation, taking the origin as A. So the moment equation will become 5 times x minus 40, which is written here. You can take start origin this B also, and the moment in that case will become equal to minus 5 times x. X will be coming here. We will be moving from B to A now. That will be our section. So minus 5 times x. So even that is taking origin at B, that will give you a simple equation as compared to when we take the origin at A. So that should be your preference. And now remember, when you are going through these slides and when you are revising this lecture, you do revise this, whatever I did and whatever the calculation is shown based on selecting these joints, A and let's say C. But you must revise this also by taking different origins and by writing the moment equations. You must be getting the same solutions, and that is the actual practice you need to do. That will give you the confidence. Now, this equation is clear now, MAB, we are writing this with respect to the origin A. For BC, we are taking the origin C. All the member and actions are 0, so it means the moment equation will be equal to 0. You can check the limits also and the i's also, because we will be needing these values again in completing the table. So here now, quickly you write down, remember this MAB, it is applicable from 0 to 8. I is I, and MAB equation is 5x minus 40. Similarly, for BC, the limit is from 0 to 16. I is 2I, and MBC is equal to 0. Origin is C. We go now to M1 values corresponding to C now. Here, if you remember, AR1 was in the vertical and it was in the downward direction. So at the same location in the downward direction, we are applying 1 kip. Summation of Fy is 0. So at B, the reaction is becoming 1 kip in the upward direction. It is causing a couple in clockwise direction, so it should be balanced by resisting moment. This is the balancing moment now, and its magnitude will be 1 times 16, so 16 kip feet we are showing here. Horizontal 0, so horizontal force is 0 from summation of Fx is equal to 0 is coming. Member BC is completely analyzed. Joint B now, it should be in equilibrium. So 1 kip upward, so 1 kip downward here. Horizontal 0, horizontal 0. 16 kip feet counterclockwise, so 16 kip feet clockwise. Joint B is in equilibrium. AB should be in equilibrium. 1 kip downward, so 1 kip at A in the upward direction. Horizontal 0, horizontal 0. 16 kip feet is the moments, resisting moment at A will be 16 kip in the opposite direction. So here we see. Now origins already we fixed. So this M1 for member AB, it will become minus 16 because it is causing tension in the outer fiber, and 0 times x will give you 0. So minus 16 you see here. And then for member BC, this 1 times x, it is causing tension in the outer. So minus 1 times x, this will become, so minus x you see here, moment, this is 0. So this is minus x. So quickly now you can write down M1 for member AB and for member BC. That is, these are minus 16 and minus x. The other information, the limit and the origin and the I values already you recorded for the capital M value, so you don't need to do that. Next now, as 2 degrees indeterminate, so corresponding to AR2 we need to apply. It was leftward directed, AR2 was, so 1 kip we are applying in the same direction. Analyzing member BC. So leftward, so here we have rightward summation of fx is satisfied. Upward and upward 0, 0 because we don't have in vertical direction any action. Moments also, this axial is not causing any moment. So member and moments are becoming equal to 0, 0. Giant should be in equilibrium. So up this vertical 0, horizontal rightward 1 kip, horizontal leftward 1 kip. Moment 0, so moment 0. Let's put this AB in equilibrium 0, so 0. 1 kip left, so 1 kip right. Now this 1 kip is causing a moment counterclockwise 1 times 8, which is 8 kip counterclockwise. It should be balanced 8 kip feet clockwise. So M to AB is equal to, now writing the moment equation. So we have 8 minus 1 times x. So 8 minus x is recorded here. Here from this, taking this origin, 0 times x and plus 0. So 0 is recorded here. M2 values are final now. Now we complete this table. Already we have the origins. Now again here, this is a mistake now. For BC, we took the origin is C. So let's now correct this. This is C. And these are the capital M values for each member, for M1 values for each member and M2 values. DRL1 and DRL2 we calculate. Now DRL1, so it is again MM1EIDX. This is contribution from member AB, and this is contribution from member BC. DRL1 25 60 over EI. DRL2 contribution from member AB. This is contribution from BC. So DRL2 is calculated. DRL1 and DRL2, here we write 1 over EI, and this is the value. Then flexibility coefficient. So we have this basic equation. F11 means M1 times M1. So directly you can write minus 16 square instead of writing this again and again. Similarly, this will become minus x square because this is M1 square now. So this again you see from member BC, you see because of 2EI this contribution. F11 is calculated. Here F12 is equal to F21. It is calculated here, and F22 is calculated here. So we have now this F matrix, flexibility coefficient matrix is calculated. Next, now compatibility equation. We write the compatibility equation. This is the format of the compatibility equation. We revise this, remember, for beam now in frames also. So quickly I'm going over this one now, the compatibility equation. And we put now all the values we have. So we put those values, this EI and EI will cancel, and AR1 is coming equal to 0 and AR2 is coming 5. 5 means our selected direction is correct. That is why we have this positive. So we put this AR1 is equal to 0 and AR2 is 5 kip now. Now rest of the values, you can do it very quickly if you use the equilibrium approach. 10 kip, and this is 0. So it means here the vertical reaction at A will be 10 kip in the upward direction. 5 kip is already getting balanced by this 5 kip. So it means the horizontal here will be equal to 0. What about the moment now? 5 times 8 minus 5 times 8 means this horizontal components moments are getting cancelled by each other. This 10 kip is not causing any because it is passing through the point A. 0 times this, so 0 times distance is 0, means the moment in this, the resisting moment at A is going to be 0. Means this member is not having any shear, this member is not having any shear, this member is not having any moment, and this member is not having any moment. We have pivot column actions in member A, B, as well as in member B, C. No shear and no bending. These are pure under compression. Here now, we start now how we prove this by using this matrix approach. So again, we are using for the member and actions AM is equal to AML plus AMR times AR. We are using this approach. Now, you can see AM 1, 2, 3, 4, 5 up to 6. These are unknowns. AML now we get from this for member AB already we have. So it is becoming 10 minus 5 and minus 40. And then we have minus 10, 5 and 0. These values are recorded here. This is from where we got the capital M values. Next, AMR first column. So it is coming. Now it is 1, 0, and this is minus 16. And then we have minus 1, 0, and plus 16. So these values are recorded here. AMR second column, it is coming from here. It is 0, 1, and this is 8. And then we have 0, minus 1, and 0. So all these values are recorded here. Now, here now, we find out the AM values by running these matrices. The AR values are given here. So we have AM 1, 2, 3, 10, 0, and 0. AM 4, 5, and 6, minus 10, 0, and 0. We put them on the member. 10, you can see 0, 0, and minus 10. So if you see here, the shear is 0, bending moment 0, shear 0, bending moment 0, only axial forces we have. So this is becoming shear force diagram. This is becoming the bending moment diagram. We do the same process for member BC. Now here we label the member and actions AM1, 2, 3 up to AM6. These are unknowns. Now AML values all are 0, 0, 0. From where? From here we record these values. AMR first column, from here we take, it is 1, 0, and minus 16. So here you see these numbers. And then minus 1, 0, and 0. So minus 1, 0, and 0. Next, second column of the AMR. So it is 0, 1, and 0. Here you see 0, 1, 0. And this is 0, minus 1, and 0. These values you see. Here AMR 6 cross 2. And we solve this equation and get the all the 6 member and actions. Now we put them on the, we don't have any member force. So now we are in a position to draw the shear force and bending moment diagram. Only axial 5 cap, you can see the shears are 0, the bending moments are 0. So just straight line 0, 0, it is showing the shear force diagram and 0 for the bending moment also. Then we superimpose them, and this is now the completely analyzed structure. And this is the shear force and bending moment diagram. 0 and 0. This completes the solution of problem number 3. Now, your assignment, now where you see this section A, this is for section B now. Section B have to solve problem 6 and 7. So you don't need to do anything with this problem. This is for section A. You don't need to do anything with this problem. This is also, but this is now your problem. You need to solve this one and problem number 7 also. You need to solve this one also. This is your assignment, and next week you need to submit them. So with this, we finish the analysis of the rigid joint 2D frames by flexibility method. Now, repetition of the process now. First, we look at the structure and we determine the statical indeterminacy. From the statical indeterminacy, we declare the corresponding now redundant actions. We remove the redundant actions and make the release structure. After release structure, we start now analysis of the release structure when it is acted upon by the actual loads, and we write the capital M equations for each member. Then turn by turn, we apply the unit redundant actions corresponding to their locations and generate the M1, M2, and so on values for their for each member. After that, we complete the bending moment equations table, which has the segments, information about the segments, their lengths, the moment of inertia, their capital M values, M and M1, M2, and M3 values. Then we calculate the DRL. One value, DRL1, is from capital M, small m1 EI dx, integral of these and summation of all the members. Similarly, DRL2, which is capital M times M2 divided by EI dx and summation of integrals and then summation of all the members. Similarly, M11, the F11, which is from the product of M1, F12 is equal to F21 from the product of M1 and M2, and then the F22, which is from the product of the small m2s. Then we apply the compatibility condition and find out the unknown redundant actions. Once those are found, after that we find out the member interactions by applying the equation AM is equal to AML plus AMR times AR. From where the AML values are coming, the AMR values are coming. Already we discussed it in very much detail. Now we put all these member interactions on the member, and the externally applied loads also, we draw the shear force and bending moment diagrams. And once that is done for each and every member, then we draw the combined shear force and bending moment diagrams. Now the time is exactly 12:46 now. We'll be taking a break now, but we can stay now. If you have any question, you can ask me the question. After that, we will start the module 4, which is about the analysis of the trusses by flexibility method. So now you turn on your mics and ask me if you have any question.